Hello guys, that's the class for Wednesday, July 6th, and we are going to start chapter 5, which is finite control volume analysis. Okay, so for homework 5, the deadline is next week. You need at least the material that I'm going to cover today, but the next class, which is Friday, is not uh, there is not any question from that because we are going to talk about maybe solving some questions about the conservation of mass and momentum, and also we are going to start teaching um, conservation of energy. But just watch this video because you need it for homework number 5. So here, chapter 5, part 1 is conservation of mass. And you know what does it mean? It means that the mass doesn't change, and except if the flow goes out or goes in, so the amount of mass should be the same. But there is something else that you have to remember from chapter 4. From chapter 4, I'm going to write it down here. From chapter 4, system, you remember from system analysis that we had control volume and system. From system analysis, in a system defined as a collection of unchanged content, right? What does it mean? It means that you can give the particles or atoms or molecules in a flow or in a fluid an identity to each, and then you can say that okay, system boundaries is somehow defined, that this is not going to change, not at all, because the boundaries move somehow with the flow, that just keep these guys in the family or inside of the space that is covered by system. So it's like a father in a family, so it's going to follow the kids because these are my kids, and I have to keep those in a family and keep those safe. So that's the meaning of system. And if you consider that the conservation equation, it means that the mass of a system should be conserved, right? And also the continuity equation means the conservation of mass, and this is also known as another name for that. So continuity equation means also means as also means conservation of mass. So two names, there are two names for that. So you can use continuity equation or conservation of mass instead of each other. So how we can find it? At first, we need to define what is the mass of a system, right? So you are going to say that the mass doesn't change with time. So how you can show it? You have to show that the total derivative of that doesn't change. So at first, let's define the mass of a system. Mass of a system can be defined in a system as rho density times the volumetric integral volumetric, and this dV, and getting integral over the system gives you the mass. What else? Here we wrote it down that the derivative or total derivative of mass of a system should be equal to, again instead of m of system we replace that with the equation of integral equation. But what it should be 0. Why? Because it doesn't change. Okay, So what does it mean? It means that time rate change of the system, change of the um, system mass is zero. That's what exactly means. So now, if we use the Reynolds transfer theorem that we talked about, because we are going to, that's again, system analysis is based on the Lagrangian approach. But the control volume approach is much easier for us because we don't want to follow the particles. We are going to answer that what is the flow behavior, not specific particles, because the flow comes in, particles are changed, and you don't want to just analyze a small box of the system, or maybe huge, but you move with that and say that, okay, I found the volume and density or whatever the parameter that define the flow. Inside of that system, we are going to talk about the control volume that is, okay, we are the boss. We are standing at the specific point in the space and wait for the flow to pass, but we can analyze it. That's the question. So at first, I remember we assumed that control volume is fixed and is not moving. So why we assume that? We assume that control volume, yes, control volume should be fixed in the space, but it's not always like that. Sometimes you need not only the mass is the system is moving with the flow, sometimes the control volume also moves, and you need to answer those type of questions. We have an example for that, and you will understand more about it. But for now, let's assume same as before. The control volume is fixed in space. Okay, so if you apply the Reynolds transport theorem, means define what is the d of the mass of a system, right? You remember from chapter 4 that how we define the Reynolds transport theorem, which is the relation between the system analysis to control volume analysis, and it's time rate change of the mass of system in control volume, and also the net rate of flow of mass through the control surface, right? So we have three terms here: term 1, term 2, and term 3. If we define that, this is going to be time rate change of the system mass, which we wrote above, but it should be equal to what? It should be equal to time rate change of the mass of the control volume plus the net, which is term 1 and that's term 2, right? What is that? Is the net rate of the flow of mass through the control surface, right? So that's the second part. And what would be the summation if the mass of system doesn't change, that we wrote it up, if you don't have any reason for that like combustion, that's something that suck the mass and change it to another product, then you can say that, okay, total derivative is going to be 0. And if that's 0, then also this is going to be 0, right? And what is the name of this equation? This is continuity of equation. Continuity equation or conservation of mass. Okay, so that's the way you can write it down, that okay, if I'm going to apply the control continuity equation, then I can apply this equation, right? What you should do, you have to find that what is the time rate change of the mass inside of the control volume plus how much of the mass is net of the mass that is going pass through the control surface. That's it. That's the whole thing that you have to do. But what assumptions we can apply to make it easier to find to solve an equation, because again the fluid mechanics is based on the assumptions, right? So what you do to make it more simpler, and we can apply assumptions, right? For example, one of the assumptions that most of the time, if that's flow is steady, and if the flow is steady, then the term of time rate change or local term going to be 0. Then the only term that is going to be left is the second term or third term here in the continuity equation, which is the integral on the control surface rho v dot n dA, and v dot n is the component of velocity normal to the surface. Then if you have only, for example, a pipe, then you can say that okay, over the wall, pipe wall, there is nothing like change because it's nothing move over the walls, but you have only input and output. Then your velocity is always normal to the input and output, and you can say that okay, what would be the m dot out and what is the m dot in, then summation of those, and deduct amount of mass that going out from the amount that is the amount that comes in from the amount that goes out, and that could be 0 if that's steady. That's how we can apply the continuity equation on the closed surface like pipe, that the wall or the shape or input output are very simple. Okay, so what else we have here? We first need to define what is the m dot, right? M dot is the unit is kilogram per second, right? Kilogram per second means mass flow rate, so that's the mass flow rate. And mass flow rate, it could be defined by using the volume flow rate. Okay, so how we had that before, that the mass flow rate is equal to density times volume flow rate, and volume flow rate is area times velocity. If you check the units, multiply that the unit of control volume times area, unit of area, and then times unit of your density, you will have kilogram per second finally. What else we can assume here? So if you have a velocity that's going out, but maybe sometimes it's not that much uniform, right? If that's uniform, then you can say that okay, v dot n going to be constant v, then over any of the area dA, I can apply that as just rho av, right? That's going to be rho av. Why we use rho av? Because we assume that the flow is uniform, and then doesn't matter which differential area you consider there, but multiplication is going to be constant, and over the whole area, then you can bring it out and make the integral easier. Okay, but how else we can do it? If we assume that in general form m dot is equal to integral over the area, which is our control surface, then rho v dot n, rho v dot n is going to be again the normal component of fluid velocity perpendicular to the area, right? And times dA. Okay, but we know that this is going to be equal to rho a v, but we can put a bar with. Why? Because it could be assumed that this term is equal to average velocity. So that's how we can find the average velocity. average velocity is going to be when the flow profile, velocity profile is not linear or not uniform. Especially if the linear, that means that it's changing over the area, differential areas. But then you can find what is the average velocity, and average velocity is going to be a rho v dot n d8 over rho a. That's the equation for finding the average velocity. So for example, if you have flow that passing through a channel or a pipe, and you know that this is going to be your flow flow profile, velocity profile, then how you can find the average? You can write it down here like your profile, and then you can say that, okay, I will get this integral. At first you need to define what is your integral area, right? Differential area. So that's the differential area and normal velocity over that, and get the integral over summation of all over the area, then over rho a. This is going to give you average velocity, and location of that is going to be center of the surface. That's the way we can find the average velocity. But for now, let's move and talk about another assumption. So we made an assumption there that the velocity is the velocity of control volume is 0. So it means that control volume doesn't move, but sometimes it moves. Okay? So it's very easy. Just doesn't change that much. For example, you have a jet here that is coming and hit the this car, and because of the jet's momentum that it has, it's moving this car. So that's the control volume. Okay, so control volume is going to be a space that you will assume that, okay, I'm going to put my control volume here because that's the screenshot of the flow, that's the space that I'm going to know how the flow moves, right? So what will happen if the item moves? Absolutely, you get a camera, you stand somewhere and going to analyze the fluid. But if that moves, you also should move, because you want to have from here to here an image or analysis from here to here, right? So sometimes that the whole flow moves, then also control volume should move. That's the part, because you want to, control volume is fixed in a space, but also it wants to give you boundaries that fix over the flow, right? So that's only like getting a camera and you are going to follow your kid. Okay, you have a child, is going to be playing, so you put your camera somewhere and going to record video from his or her playing. Okay, so what will happen if he is going to out of the camera view? Then you need to turn the camera, right? It's again a space, it's fixed in a space, but what is the main object that you are going to analyze? Is your child. And where is the flow? Is here. If it's moving there, then your control volume should move. So what will happen for the continuity equation? Nothing. You only need to, instead of velocity that the flow has, you use the relative velocity. So you have a velocity here that flow comes in and goes out, like v, so v1, and also here you may have another v. Okay, so you have another you have a velocity that is flow, and we use that for continuity equation previously if this is fixed. But if it's moved, then you have a relative velocity between these two. Okay, so you decrease the velocity of flow to a relative velocity and apply the continuity equation. That's the only thing that you need to do. Continuity equation is still valid and nothing going to change, just only you need to use W, which is the relative velocity. Okay. What will happen? So again, you can say that I think again the control volume is fixed, so V0 is going to be 0. But instead of considering velocity here as V, I will consider as W. So I will assume that this is my velocity. So it means that you have a camera, your object is a car, you get the camera and getting figures, or we record the video from the car, okay? And car is standing somewhere and stopped. But when it moves, you also in another car moving with it, okay? Then you have a relative velocity. You want to see the car, but at the same time you also should move with it because it's going to go out of the view of your camera, right? So then your car, maybe your car, that your object is the velocity is 100 miles per hour, and you have 98 miles per hour, right? What you see in the camera, you see that the car is moving with 2 miles per hour in a direction. Okay, that's what you are going to analyze with your camera. Here is the same. So instead of considering the flow passing with velocity of v, you will consider that the control volume is fixed. There is no velocity here, only what is the input, output, or whatever the flow is. What is the relative velocity, and replace it here in your control volume. Okay, so I'm going to talk about something much important than moving control volume and this stuff that is mostly mathematical based. So I will, if I ask you to change this equation, because you have two integral, change it to one integral, you are not allowed to do it, because one of those is control volume and one of those is control surface, right? So you have a second order integral, you have third order integral. So we'll show it with the surface like 2 over the surface, and you will show it with 3 over the volume, right? So this is going to be your volume, and that's going to be your surface. Over the surface and over the surface and over the volume is not going to be mixed or merged. Okay, that's hard. Okay, you cannot fix it, you cannot merge these two. But again, in fluid mechanics, you want to make it simpler, right? That's why that's where the mathematics comes in and help us. How? Using divergence theorem. So what is the divergence theorem? Divergence theorem is a theorem in mathematics that you don't need to know how you have to prove it. Just use that, because it's going to be sometimes proving a theorem is sometimes very hard. Okay, so divergence theorem changed the surface area, the integral over the surface, to integral over the volume, using a gradient and divergence, getting the divergence of that term. So how it changed it? Divergence theorem first change the surface integral into volume integral. Okay, how? By using this equation. First, over the surface, if you had any f dot n ds, it would be equal to over the volume, okay, over the volume of that gradient dot f d. So if you apply that in any thing that has f dot n over the normal component of any parameter or any vector, normal to the area, then you can use the divergence theorem and get it a volumetric shape of it. Okay, so how we can, if we apply that, what will happen here? It's easy. In the continuity equation, so the first term, which is integral control volume, which is rho dv, so we keep that. Okay, so we'll keep that, nothing going to change. But the second term, which is the rho v dot n ds, rho v dot n ds, so just rho is here, that's going to be out of the v dot n and going to be considered after that. But if you say that, okay, rho v dot n, rho v is going to be your f. So what we should do, we should do like control volume first, because we applied that control volume divergence theorem and make it control volume, and the differential, the integral going to be over the dv. But what would be here is gradient dot f, gradient dot rho v. So why we did that? Because we are going to merge these two and say that, okay, now I can write it one integral of control volume, then write it down that one term, because now I can sum up these two. The dv is same and the integral of both control volume or over the volume. So round of the d round rho t plus gradient dot rho v dv equal to 0, if that's the continuity equation, right? So now I change that to this stuff. Okay, I will show it again how you can make it more simpler and bring the rho out with some assumptions. But for now, just keep it that how we can merge these two integrals, that one of those are control volume based and the other one is control surface over the control surface, into one integral using the divergence theorem. Okay, till here I wrote it down that how we can bring the rho here out and merge with this one, but in the additional topic, because it's not part of this chapter. Only I need to give you a hint, because I'm not going to teach chapter 6 for this course. We don't have time for it. So just only two, the most simpler part, but the most important one that you have to learn in this course. If you say that you are going to pass fluid mechanics, you have to know it. And that's two term is dilatation rate and vortex and the angular velocity of component. We'll talk it later. So till here we talk about continuity equation. Okay, now what's next? Next is Newton's second law, which is linear momentum, and we say that, okay, rigid body motion is valid here in the fluid mechanics, so we are going to apply that over the fluid, and again over fluid particle, and then using those system or Lagrangian approach, using the transport theorem, Reynolds transport theorem, bring it expanded or extended to the whole flow. Okay, that's how what we are going to do. First, linear momentum is going to show that it's based on the rigid body motion, that the time rate change of the linear momentum of a system is equal to sum of the external forces acting in the system. Okay, that's a Newton's law. If you have a net force, then the momentum going to change in the direction of that you have a velocity. You have the force there. Net force direction is going to change your momentum in that direction. That's the meaning of Newton's second law. Okay, so in the fluid mechanics, you have to define that for a small particle. Okay, we are coming to say that, okay, a small particle or fluid particle is a rigid body, and now we can apply that over the rigid body. Okay, so first give me that what is the mass. That's dm. Okay, because we assume that this is very small particle. What is the momentum of that? dm is going to be the name of momentum is capital P. We wrote capital P because the book used that, and momentum is a vector, right? And is equal to dm times velocity. It has to be vector because mass is scalar, and dmv velocity is vector, and if you multiply this, you will have finally a vector. That's why momentum is also vector. But dm could also be replaced by rho dv. Okay, so if we use these, we can have momentum of that small particle, that is p, equal to rho velocity dv. Okay, so if our system moves with this particle, then we say that okay, the momentum also over the time, the total derivative of that should be 0. Okay, or should be equal to the force, right? Because that's mentioned here for rigid body motion. Then we can say that d over dt of p, or momentum, should be equal to net force acting on the fluid particle, right? That's valid because that's the meaning of second Newton's law. Okay, so in this system, we can replace the net force with the m of the time acceleration of the system, right? And you can write that okay, sigma of all the forces, which is our net force, is equal to d over dt of integral over the system of rho velocity and dv. That's what we can write it down here using the Newton's second law. And what else we need to do? We need to use the Reynolds transport theorem, transfer, which is or move from system analysis to control volume analysis, or Lagrangian approach to Eulerian approach. Find this equation like this one, and then we can also apply the divergence theorem and merge these two integrals and have a final equation for control volume, right? Again, both of them are going to work. Mostly in the homework that I gave you, you have to use the dA form because that's much easier. But control volume base, or merging these two, are going to give you the Navier equation that is for chapter 6, and we don't have time to cover that right now. But you will see different view of the different version of the continuity equation, and since those are highly mathematical with the terms, it makes you mix these two, that oh, these two are different, but these are not different. These are only using the mathematics to merge the integrals and rewrite the equation. But again, the meaning of that is the same: continuity equation and momentum equation, or based on this first and second Newton's law. So here, what we can do here, we can apply Reynolds transport theorem on the equation that we have. Okay, so if you apply that, then the force over the control volume is equal to the time derivative change, time rate change of velocity, or times the momentum in the system control volume, and plus the amount of momentum that pass over the surfaces. Okay, so this is the same, and then we can apply the divergence theorem and have a better shape of it, that is merging these two. And again, you can write that sigma f of control volume is equal to 1 integral of control volume, then bring the rate into the equation, and you will have v rho, or rho v, doesn't change anything, and then plus gradient, because this is going to be your f now, and gradient dot v rho v, and finally all times dv. That's it. You merge these two integrals. Okay, also mathematically you can bring one of the rows out and make it more simpler, but right now don't worry about it, because it's not part of this chapter or any part of this course actually. Okay, so what else? We are going to define what is the forces of control volume. Okay, what type of forces going to be act on control volume? Okay, we have two types, or sometimes you have you can assume that it's three types, but generally it's two types: body forces and surface forces. So the sigma of CB, or control volume, is two types generally: the surface based forces and body forces. For example, pressure force is type of surface force. Tau, that's the friction type force, is surface force, but weight of the fluid is a type of body force, right? These are different type of the forces, and all has to be sum up, and the net of those should be equal to change in linear momentum in the control volume, which is equal to the force or net force acting on the control volume, that we write it down here. Okay, so again we are going to talk about assumptions. What is the first assumption that we can apply here? That if the flow is steady, then the time rate change of the linear momentum is going to be 0. Okay, what else? Just defining the forces, then we can write it down. What is the amount of the net flow of the momentum over the control surface? Then the sum of all is equal to the acting the net of the force, or on acting on the control volume. Okay, so here I'm going to, in this example, that simple example, I'm going to write it down, the different type of forces. That's why you need to analyze. First, define your control volume. Okay, that's the first thing that you have to do. First, define the control volume, and we show it with this. Okay, that's my control volume. What is the control volume? You are going to, that's also part of the question, how you define the control volume. You have to decide that where is your, you have to put the boundaries, and what is the space that you are going to analyze. Sometimes just defining the control volume change your question from a very simple question to a very hard question. If you define the boundaries in bad way, then analyzing that is mathematically very hard, or sometimes impossible. but only with moving those or putting the boundaries in the correct point or right point you can make assumptions that is very simple and make the solution or the solving that question very simple. First, define your control volume, and we write it down here with the red dash line. And let's write that what is the okay. So velocity comes in, comes out. You have a pressure 2 here, pressure 1 here, and you may have the tau at wall. Okay, so tau at the wall is the force is on the fluid act on the wall in this way, but the reaction of that is going to apply on the fluid in that way. So that's type of reaction forces. That's why sometimes they make categorize the forces into 3: surface forces, body forces, and reaction forces, reactive or external or reaction forces. These are not different. The tau is also part of surface force. In general, you have body force and surface force, most important one, and tau or friction force is part of it. Okay. So, what are the forces here? First, also another force that we have is the W of fluid, which is gamma v. Okay, that's the weight of the fluid. So body force in this case is fluid weight and surface forces are one is P1A1, which is here, right? That's the pressure at this area, and it's going to be in this direction. And another one is here in that direction. So P1A1, P2A2. Also another type is tau of the wall, or tau here, times the whole area of the wall, right? And also, what else you have? If that's your control volume, you shouldn't say that you have a wall here. In the analysis, you will understand that, okay, I have a pressure here, right? And also I have a pressure here. If you have a atmospheric pressure all over the space, then you have a pressure force on the wall and also on the control volume, right? But all of these are going to cancel out each other. That's why we don't consider any atmospheric pressure, because also you have atmospheric pressure here and here. Then you don't need to assume that, as long as that the atmospheric pressure is everywhere. Then these are going to be your P on the wall, or pressure force on the wall, and here also you have it, but the summation of all going to be cancelled out, because one of those has a corresponding on the other direction. That's all the forces. Why we wrote it down here in an example? To show you how you can analyze a case, right? That's an arbitrary shape or arbitrary channel, and you have to find out which of the forces are acting here, and then based on these two surfaces that you have, because control volume are going to be boundaries are here, then let's say you have a circular shape, right? So A1, A2, then you can apply the the momentum equation, okay? So how you can say that, okay, I will write down all the forces here. That is, first you need to assume what is x and y, right? So I'll assume that x and y are here. So that's my x, that's my y, okay? And because that's a direction base, you have to write it down what is in x direction for example in x direction, what is my uh, uh, forces, right? So one force is going to be P1 V1, it's simple. Sorry, P1 A1. Okay, what else? One component of velocity of P2 A2, if that's the angle, there is an angle here, right? So it's theta. So for example, the another one is on the other direction, so it's going to be another force in this direction, right? So this is going to be your component, and it's going to be negative, right? So minus P2 A2, if that's theta, so that's going to be your theta cosine of theta. Okay, that's also another force. What else? You have to sum up all the tau, and if the angle you have of arbitrary shape, you have to get the integral over the area, so it's going to be negative all over the area of the wall, tau wall times dA, right? And get the integral of that. What else? You have the fluid, right? But the fluid in y direction. Also, one of the components in y direction is the pressure forces. You don't worry about those, because that's only writing in x direction. And what else? Now you have to write that how much of the momentum changing over the control volume. Okay, so since that's a steady and you assume that it's a steady, then the first term here is going to be 0. What about the second term? You have to write it down, that how much of the force are going to come in and goes out, right? So if that's velocity, then you will see that the n here is going to be in this direction, right? So v dot n going to be negative, and minus rho v1 squared times the area of 1 is going to be the amount of momentum that comes in with negative sign, plus here is going to be positive because n and v are in the same direction, and rho v2 squared times a2 are going to be the amount of momentum that goes out, right? So that's it. You are going to, you have an equation here, then you can find, for example, what is the velocity that is going in or goes out. That's the way you can solve question here in chapter 5 based on the continuity and momentum equation. So in this part, it's much easier to use the surface without the divergence theorem here, like the first one. But using that is going to be hard. So that's why we have two versions of that, and you have to decide which one is more easier to be used based on the question. It all depends on the question. But for this chapter, and absolutely for this course, you will mostly use the first one. This is going to be only for you to know more about that and for your future, but this one is mostly used because the questions that we are talking and in the exam and also in homeworks, it would be much easier. And don't worry about that if you couldn't understand this part, but you will need it in future if you are going to do research in this area. Okay, so I told you before, the fluid mechanics is based on assumptions. Okay, what does it mean based on assumptions? You have to do assumptions and make it simple. That's it. That's whole thing about the fluid mechanics. Okay, so the comments are going to help you to solve a question in this chapter. Okay, at first you have to identify a control volume. It could be the entire device, it could be the fluid, it's based on your assumption, and it's your question and your solution. It depends that how you are going to solve it and what is the control volume you have to decide. But by solving different questions, you will know more and more how you can define the control volume. Then you need also identify coordinate system. Why? Because you can define that which is the direction, and if you remember from the question that the example that we saw for the arbitrary channel, you will need it because these are velocities and momentums, and those have a direction. So everything is based on direction. What else? You can assume can have possible assumptions like a steady state, no variation over time, so that term is going to first term going to be zero, or you can say that okay, density is constant, then the flow is incompressible, then I can make it easier, bring the rho outside. And what exactly I did in the question, so I assume that the flow is uniform, then rho v squared, I bring the velocity out, the area out, and make it more simple. Okay, so here also this is one of the assumptions that I applied, that is the flow is one dimensional and is not changing across the section. So that means the flow is uniform. If the flow is uniform, the velocity all over the cross-section area is equal. Okay, so this is going to be uniform velocity profile. But sometimes you don't have it. You may have a non-uniform one, right? If you have a non-uniform one, you can assume the average velocity somewhere there and make it easier, or you have to get the integral and solve it mathematically. But all it depends to that. What else we can do assumptions and make it easier to analyze a system of control volume is that linear momentum is directional. So the direction of fluid, it matters when it's going out, going in. Then you have to know that the same as before, when v dot n is negative, right, then it's for inflow, and if v dot n is positive, this is outflow. The same as before. We applied that for chapter 3. And what about the forces? Direction of external forces with respect to the coordinate system, right? That's the example that we wrote it down. We solved that for arbitrary shape, but here we make it easier and rewrite it here. That if you have a channel or pipe like this, and that's your negative, so at first define what is my control volume. So I'll put my control volume here inside of the pipe, okay? And let's say that this is not output, that's a long pipe, only we have output here, okay? So you have only one velocity here. Absolutely, you have if you consider you have a boundary velocity here for control volume, you have to also assume that you have another velocity down there. But it just wants to make it easier and just solve for one of the surfaces. But yes, when you close your boundaries here, you cannot assume that it's infinity and it's going to go for a long pipe. You have to cut it somewhere, and that's your control volume. You are limited in the space, and you have to assume that where is your control surfaces, and since you have a velocity comes in, then you have a system or a control volume is fixed, a control volume here, then you are going to analyze that. But if you have an angle here and you have velocity there, okay, so this velocity has two components, Vx and Vy. As you can see, if I assume that this is my x and y, then Vx is going to be negative, and here Vx is going to be positive, Vy going to be positive. The same here when it comes in, okay, two components of velocity. So if that's V1, we can write it V1 and then V2 here, for example. Okay, so this is going to be 2x and V2y. What else? This is the negative direction, okay, in x. So you can write at first what is the components of velocity, right? You can write it down, that is vxi plus vyj, okay? So just for consider that I'm writing that for v1. These are only examples, okay? So what would be vx? Vx going to be minus, because that's negative direction, the magnitude of the velocity times cosine of theta. If that's theta, then this is going to be your theta, and v is going to be amount of velocity times cosine of theta. And what about vy? It's going to be amount of velocity times sine of theta. Alright, you replace that, and in integral form you can apply that in x and y direction. How? You assume that this is a steady state flow, okay? So just applying for output. We'll talk about input and in the whole question later in the examples, but let's apply just for output. So you can say that the time derivative change is 0, and then only rewrite the second integral, which is the control surface, right? So the control surface term is v, velocity, rho v dot n times dA, right? So if you write it down here with the amount, so v is going to be amount of v, rho is going to be rho, v dot n depends to the direction. So if you write it down for the x direction, then it's going to be minus v cosine of theta, right? And what is dA? If you assume that I'm using the uniform velocity profile here, then I can multiply that by the area, right? So here in this output you have one term in x direction. What you have, you will have one term which is multiplication of all these, minus v cosine of theta. I will write it first, then rho a v. Rho a v is your m dot, right? And this is going to be your vx. Then in x direction you will have m dot vx. What about the y direction? You will have m dot vy. The same, the multiplication of this term, sine of theta, times rho a v. That's for the second. That's it. For now is enough. We'll solve a bunch of the questions the next class. I'll show you how you can apply it in a real question and how you can make it simpler and solve. But before the end of this class, I'm going to talk about two additional topics here. One is meaning of incompressibility. So what is the meaning of incompressibility? Incompressibility means the flow density does not change, not with the space and not with time, okay? So it's totally incompressible. Means the rho is constant everywhere in the flow and also over the time. So rho is constant, then all the derivatives are going to be 0. Perfect. So you can apply this, right? Let's write it down, the continuity equation here. If you write it down and apply the divergence theorem, you will have one control based on control volume, one integral, right? Time derivative plus gradient dot rho v in the dv is going to be 0, right? Since the rho is constant, and if you assume that the rho is constant, okay, then you can say that, okay, all derivative change is going to be 0, and also rho is constant, it comes out from the gradient. This is going to be 0 because the flow is incompressible, and also rho is constant, comes out and what you will have finally, you have rho gradient dot v. Okay, so this is 0, and if the integral is going to be 0, then the only term that you have should be 0, right? If that's 0, then we can write it down that, okay, rho gradient dot v is going to be 0, and since rho cannot be 0, density is not going to be 0. Density, if means that density is 0, means that for a volume of the fluid, your weight is going to be, or mass going to be 0. That's not possible for a material. It then means that you don't have anything there. Okay, so it's not cannot be 0. Then the only term that is 0 is gradient dot v, which is volumetric dilatation rate. Okay, so that's simple till now, but it's very important. How? Because when you have a velocity profile, if you get the gradient dot v, or finding the volumetric dilatation rate, and if that's 0, you can assume that the flow is incompressible. And it's not 0, you can not say that. You can say that it's compressible, right? For example, the Brillouin velocity profile is given. Velocity profile is 2xy, nu is minus x squared y, and w is 0. Just assume that it's 2D. So that's an example. So it asks you that is the flow is compressible or incompressible based on the flow velocity. So what you should do, you should check the volumetric dilatation rate and find it. Okay, so gradient dot v is rho u over rho x plus rho v over y and rho derivative of w versus z. What is the derivative of u? In x is 2y, right? Derivative versus x is going to be 2y. And what about this one? Versus y is going to be minus x squared. So the answer, and also this is 0. So that would be 0. What would be the answer? 2y minus x squared. It's not 0. Absolutely, if y and x are 0, it means that for a single point in a space, yes, it would be incompressible. But we are not talking about a single space, single point. We're talking about the flow. Flow has a space, it has time, and you're not getting that. Only for one point, yes, mathematically in one point in the space, this is going to be compressible, but not generally. Okay, so we'll answer that yes, the flow is compressible because the dilatation rate is not 0. Why z being 0 means compressible? It comes from the equation of continuity. So we found out and proved that if the rho is constant, then gradient dot v is going to be 0. Okay, so that's the divergence of the velocity is 0. So another example is also given. U is minus x squared minus x times 1 plus x, and vy times 2x plus 1, and w is 0, right? So now he's asking you that is this one compressible or compressible, asking based on the velocity of profile or velocity components of velocity. Then again you will check the dilatation rate, and again because w is 0, I'll put it out and get the integral and get the derivation and find that it's 0. So that's incompressible. That's the way you can find out that the flow is incompressible or not, only based on the continuity and using the dilatation rate. Okay, that's one part. The other meaning that I'm going to talk about is it's not vorticity now. Vorticity is going to be complex, but is finding the angular velocity. Okay, angular velocity, or meaning of rotational irrotationality of the flow. Okay, so we have two things. Let's say you are running. Okay, you're running in a track field. Okay, so you have a rotation when you are running. So assume that you are a particle in a fluid. You are a particle in a fluid and you are running over a track field in like a professional. Okay, you're fast moving. Because of turning of the track field, you are turning as well. Okay, that means the flow is circulating. Okay, so you have a circulation there because you are moving like turning. Okay, since you are doing the turn, I'll write it down here. That's my track field. Okay, and you are running over that. Okay, since you are running here and for a constant point that stand or someone that like your friend that's standing here, it sees that you are turning. Okay, so you have a circulation, but that doesn't mean that you are rotating. Okay, the meaning of rotation and circulation are different. Circulation means that in the flow has circulating over a center, and you can write the radius there. Okay, but if you running over this field and at the same time you're turning around yourself and running, this turning around yourself is going to be rotation. Okay, so here I wrote it down for a particle. So particle may have moves in a way, okay, that may have a velocity in arbitrary direction, and also maybe in zoom out you have a circulation like moving like turning. Okay, that doesn't mean that you for sure your flow is rotational. Rotational means that in a point or in a single point or general, the component or particle of velocity are moving around itself or moving around or turning around its directions, right? So if the particle has an angular velocity over any of the its main direction or axis, then you will have a rotation there and the flow is rotational. Okay, so if you see that the sink, for example, you have a sink and the flow are going over the sink hole and turning like that, this is circulation. It doesn't mean the flow for sure the particles of the flow are turning around itself as well. No, they are not. They are moving like smoothly turning over the general direction, but and only if they are turning about any of their axes, then your flow is rotational. Okay, so that's the meaning of rotationality of the flow. But how you can check it from the find out that the flow is rotational or irrotational using the velocity field. Okay, that's the question that's going to answer that. At first, let's talk about the parameters. If you have a z, y, and x direction and you have a rotation over there, then you have an angular velocity. Okay, so angular velocity is going to be shows by omega, and if you have x means that you have a rotation over the x or y or z. Okay, if that's a clockwise, then the angular velocity, that's just assumption, but all the books use that. If that's clockwise, then it's going to be negative, and if counterclockwise, it's going to be positive. Okay, but the question is how can we find that flow is rotational or irrotational? Okay, it's easy. If the angular velocity are 0, then the flow is irrotational. But if any of these are not 0, then absolutely is rotational. Okay, so mathematically you can find out the omega, which is your angular velocity, by getting the curl of velocity, and you need half of it. That is your half of it is going to be your angular velocity. Okay, so it's going to be the omega is going to be a vector omega x, y, and z in I, j, and k direction, and it's going to be curl of velocity. Okay, so the curl is gradient cross v, and gradient cross v calculated by determinant of this matrix, which is ijk rho over rho x, rho over rho y, and rho over rho z u v w. Don't need to be worried about that because I wrote it down here. You can just write this equation. I will give you in the right now you have access to the notes for the homeworks, and in the final also you will are allowed to bring a equation sheet, and you can write it down, and also you can bring I also give you equation sheet, give you all these equations. So that's the simple part. If you don't know how to get the determinant for a 3x3 matrix, just again Google it and find it in the mathematics books, that how we can get that. But here would be your equation for 3 omegas, omega x, omega y, and omega z. Okay, but again the omega is going to be half of it, right? So this is only the curve, but omega is going to be half of it for each, multiplying 1/2 on each of these terms. Okay, so example, we're going to ask you that velocity fields given as below: vx, vy, and w is 0. Is the flow rotational or irrotational? The answer is that you use the omega and find out what is the amount of each. Okay, so write it down, the equation that you have here, by multiplying by half, but doesn't matter because again the half doesn't change anything here. It only give you the amount, correct amount, but here when you are going to check that is 0 or not, then having a half here or not, it's not changing. But please keep that because that's correct equation for W, or I'm sorry, omega, that is angular velocity. So since W is 0, then I can say that the all derivative of W is 0, right? So I have one here and one here. I make these two 0 because W is 0. And also I found out that U is not function of Z, and U and V, none of those are function of Z. So V, derivative of V versus Z, and derivation of the U versus Z are both of 0. So I say that if the flow is 2D, then I have only rotation over the Z axis. Okay, it makes sense because the flow is a 2D. Then if it moves in this way, then it's not moving in the Z direction. The only can turn around itself is going to, if it's going to turn around itself, is going to be because of the velocity that it has in X and Y direction, and it gives you a rotation down there. But if you have a rotation down there, then the rotation would be around Z, right? So that's why we only have, for the 2D flow, that only has X and Y direction velocity, component of velocity, then absolutely the first and second of the omega, terms of omega, is going to be 0, and only the last one left. Okay, so you have to find what is the 1/2 rho v x and over the y. By getting the derivation, so we find that the omega x and omega y is 0, and omega z is 1/2. Getting the derivation of v versus x minus 2y, I wrote it down, and u versus y is minus 2y, but you have a negative sign between these two, and if you put there, you find that it's 0. If that's 0, you will find out that omega x and omega y are 0, and omega z are 0 based on the cancellation that we have here. Then the flow is rotational. That's the way you can find out the flow is rotational or irrotational in using the velocity field. Okay, so I guess we have to stop here for today is enough. I will post it in the YouTube channel, and next week, I'm sorry, Friday, the class for Friday, we'll talk more about some examples first, then moving to conservation of energy. Thank you for listening, guys.